Previously, we've learned about integration by parts, and we say that if we see the multiplication of the two functions inside the integration, we should try to use the integration by parts. So the formula of the integration by parts looks like this. So if you have got the two functions, f of x and let's say g prime of x, the multiplication of the two functions, then you need to use this formula in order to get rid of one of the functions. So we wrote down this formula in terms of the different notation like a u, dv, and then this is equal to this part. In this lecture, we're going to try to do four examples, and try to figure out what is actually the general algorithm or some tips about the integration by parts. So we're going to consider these four examples. So I would like to define kind of like a periodic or iterative functions. Like, so for me, the cosine of x is kind of periodic in terms of the differentiation. I'm going to explain you what does it mean. So if you take the derivative of the cosine of x, I'm going to have the sine of x was the minus. If I take one more time the derivative of this function, it's going to be minus cosine of x and so on. So no matter how many times I'm going to take the derivative, this cosine and sine, the trigonometric functions, are still there. So this is the same for the e power of x. So let's say I've got the g of x, which is equal to the e in the power of x. No matter how many times I'm going to take the derivative from the e power of x, I'm always going to have the e in the power of x. So in this lecture, we would like to discuss, hey, if you've got the multiplication of the two functions inside your integration, then you should try to use the integration by parts. But the main question is that which function is going to be u and which function is going to be dv. And in this case, I would like to give you a small tip that you need to try to use always the non-periodic functions as a u. I mean, like you need to try to denote the u, the function which is going to be eliminated in the second iteration. So I call this as a second iteration for the formula of the integration by parts. So this is our first integration. So we're going to rewrite this like this, but still we have to do some integration, and we hope that the second integration or the third one is going to be more easier than the original one. So in the second iteration, so we need to get rid of one of the functions. So it's better to choose some non-periodic functions as the u. So let's start with the first example. The first example says that we need to try to integrate the x multiplied to the cosine of x. So what's a kind of periodic function here? That's a cosine of x, right? So we know that if you take the derivative from the cosine of x, then it's going to be minus sine, then the derivative from the minus sine is going to be cosine. So the cosine sign is always going to be there if I would choose u as the cosine. So my intuition tells to me that I need to choose the u as the x, and dv should be equal to the rest of the things inside the integration. Basically cosine of x dx. Then I have to do a little bit of techniques, like I need to take the derivative from here. It's going to be du, so let me use the same colors. Du is equal to the dx, and I have to take the antiderivative from both of the parts in order to find the v. It's going to be plus sine of x. Then this integration, the original one, is going to be equal to u multiplied to the v minus the integration of the v du, right? So let me rewrite the first integral as the multiplication of the uv minus integration of the v, which is sine of x, multiplied to the du, which is dx. So do you see in the second iteration, our integral is becoming easier than the first one. In the second iteration, I don't have the multiplication of the two functions anymore, and it's going to be easier for us to integrate this. It's going to be x multiplied to the sine of x. So the integration of the sine, it's going to be minus cosine, with this minus it's becoming plus cosine of x plus the constant. Well, let's try to do this second example. In the second example, I've got this integration of the x multiplied to the e in the power of x dx. Again, so I've got the multiplication of the two functions, and I need to choose which one of them is going to be u and which one of them is going to be dv. And I would choose as a u again the x, not e in the power of x, because I know that the derivative of the x is going to be 1, or it's going to be eliminated after some iterations, while the derivative of the e in the power of x is always going to be there. So let's try to do this problem. So here again, I'm going to choose the u as the x, dv, it's going to be e in the power of x, dx, du is going to be dx, and v it's going to be e in the power of x. So then again, it's going to be uv, v du. So this integration is going to be equal to u multiplied to the v, which is x multiplied to the e in the power of x, minus the integration of the e in the power of x multiplied to the dx, which is going to be simply e in the power of x, right? So it's going to be x e in the power of x minus e in the power of x plus the constant. So again, so the main thing which we have to learn from here is that it gives you some insights about how you need to choose the u and dv, right? So you need to try to choose always a u, the function which is going to be eliminated after some of the iterations if you take the derivative. So sometimes the integration by parts is used when you don't have the multiplication of the two functions. For example, when you need to integrate the ln of x, right? So we know what's the derivative of the ln of x. It's one of the beautiful derivatives in mathematics and calculus. The derivative of the ln of x is going to be simply 1 over x, and or obviously the integration of the 1 over x is going to be ln of x. The problem is, what's the integration of the ln of x? So it appears, even though we don't have the multiplication, we need to try to use the integration by parts, and in this case it extends the applications of the integration by parts for more of the cases. So mostly we need to try to use the integration by parts if we see the multiplication of the two functions, but sometimes even if we don't have the multiplication, we need to try to use the integration by parts. So here I'm going to use so I need to denote everything inside this integration as the u in dv. I'm going to split them. So some part is going to be u, some part is going to be dv. So the thing is, I need to choose the function as the u so that I will be able to take its derivative, and dv should be the function so that I will be able to take its integration. So I don't know how to integrate the ln of x, so that's why I'm going to choose u as the ln of x, and dv it's going to be the rest of the things, which is here. So if this part is the u, what's going to be dv? So the only thing which is left here is dx, right? So I'm going to find a du, which is going to be the derivative of the ln of x, which is going to be 1 over x multiplied to the dx, and v it's going to be simply x. Again, I'm going to write as u multiplied to the v minus v du. So let me write this. It's going to be x multiplied to the ln of x minus the integration of the x multiplied to the du, which is 1 over x dx. So x and 1 over x are going to be canceled, right? And you will just have the integration of the 1, which is simply x. So it's going to be x multiplied to the ln of x minus the integration of 1, which is x, plus the constant. And the last example, which is my favorite one, is like when you have the multiplication of the two functions, and both of the functions are periodic in terms of like they don't just like vanish when you take the derivative. The problem number 4 is the integration of e in the power of x multiplied to the sine of x. Good. So we need to figure out what is this. The thing is, again, so if I choose u as the e in the power of x, it is not going to eliminate in the second iteration, in the second integral. If the u is equal to the sine of x, it's still going to be the trigonometric function in the second integration. So then what we have to do. So I'm going to show you this fascinating example. So we need to try to do twice the integration by parts, but we need to be really careful while we are doing this. So I'm going to denote e in the power of x as a u. dv is going to be obviously the rest, which is sine of x dx. du, it's going to be e to the power of x dx, and v is going to be equal to minus cosine of x, right? Then we have to multiply the u to the v, then v to the du. So this is going to be equal to e to the power of x. So I need to put the minus here. Multiply to the minus cosine, which is here, plus, right? So v du becoming cosine of x e to the power of x dx. So this is what I told you in the beginning, that this is our second iteration, second integration, where I have both of these functions again, right? So I have the trigonometric function and exponential function again. So what we need to try to do this is that we need to integrate this again using the method of integration by parts. So u in this case is going to be e to the power of x. So please note that you cannot choose the cosine of x as a u in this case, because you will just come back to the previous case. So you need to just continue and try to hope that you can figure out how to find the answer, how to evaluate the integral, the original integration. So dv is going to be equal to the cosine of x dx. du is equal to e to the power of x dx. V is going to be equal to the plus sine of x, right? So it's going to be u multiplied to the v minus v du, right? So it's equal to e to the power of x multiplied to the sine of x minus the integration of the sine of x multiplied to the e to the power of x dx. Yeah, the problem is I have again in the third iteration, I've got again the trigonometric function. Yeah, that might be a problem, right? So let's look to our iterations, what we have started. So we've started from this integration, we've got this 2, then we expanded this integration, we've got this term, right? So let us write down everything from the beginning. So we say that the integration of the e to the power of x multiplied to the sine of x dx is equal to minus e to the power of x, so this term, right? So cosine of x, so plus this integration, which is equal to this term, plus e to the power of x sine of x minus the integration of the e to the power of x sine of x dx. So do you remember? So we just need to find what is this integration. So I have the same thing here, so I can put this term to the left, and I'm going to have 2 multiplied to this integration, e to the power of x sine of x dx, which is equal to the e to the power of x. If you take out the e to the power of x, what you're going to have here is sine of x minus cosine of x. And obviously, if I would like to evaluate what's going to be this integration, I just need to divide everything here to the 2, and that's going to be my integral. So this is one of the interesting cases where we never give up when we're doing the integration by parts, but we need to be really careful because so I need to choose the e to the power of x here as the u and e to the power of x here as the u always, so that I will figure out what's going to be the answer at the end. So this were the examples of the integration by parts. So in the next lectures, we're going to discuss more integration techniques.